Sorry to everyone for a few technical difficulties, and sorry to the Zoom audience, but hopefully we have them sorted out now. So Reggie calculus is easy to picture in 2 dimensions, but gets much harder as you go up higher and higher in dimensions. So it's nice to do that one step at a time so you can see some of the salient features as you go. In 2D, it becomes clear that curvature is concentrated 2 dimensions down from the pieces that you're gluing. You see that the curvature was concentrated at that vertex while we were using 2-dimensional triangles. In 3D, a dynamical symplectic structure becomes apparent. If I'm going to glue tetrahedra around the core, like the slices of an orange, the way that we get curvature is we remove one of those slices and glue the remaining faces. And so curvature is concentrated on 1-dimensional bones. But the curvature angle is the measure of curvature, and a beautiful thing is that that length and curvature angle are symplectically conjugate. So you're able to see the dynamics starting to emerge there. However, in 4 dimensions, it becomes very difficult to picture. So let me just give you a quick guide how this works. In 4 dimensions, we glue 5 tetrahedra together, just as you would glue 4 tetrahedra to build 4 triangles to build a tetrahedron. We glue 5 tetrahedra to build what we call a 4-simplex. And the curvature is concentrated again 2 dimensions down on the triangular faces along which tetrahedra are glued. Here, the symplectic aspect, the dynamical aspect, becomes a little bit more subtle. You have different choices. The natural choice that people often work with is the length of edges as a metrical variable, because that's what we usually think of the metric as telling us. But the length of edges don't have a nice simple conjugate variable. It's a complicated combination of angles that's very hard to work with. So a second choice is to work with a metric that describes the areas of triangles. And here, once again, the angle that goes around that triangle in 4 dimensions is symplectically conjugate. And so you have a nice set of dynamical variables to work with. The second choice is what we focus on in the set of approaches known as loop quantum gravity, and it's what I'm going to focus on a lot today. In particular, that's what we'll use in the discrete geometry path integrals that we call spin foams. So my approach for you this morning is to sort of oversimplify things. I really want to build a common language that we can discuss things in, and hopefully the discussion will get more and more sophisticated as we go through the week. But I do want to warn you that I've drastically oversimplified things. I'm going to try to identify some difficult problems and some ideas that we in the quantum gravity community use. Yeah?
I'm terribly sorry, but two people can't see the slides changing. Could you stop share and start sharing your computer again?
Absolutely. No problem. So in particular, because of these oversimplifications, I'm not going to be presenting a full calculational framework to all of you. But I think it's okay. I think what I'll do is build enough groundwork that if you want to go and do a spin foam calculation, you'll be able to quickly get that from people here at the meeting. This is a lovely framing that I steal from Eugenio Bianchi here. This is the black hole entropy formula that you all know, the Bekenstein-Hawking entropy. But most of the time when we write this formula, we suppress all the physical constants in the formula. And when you restore them, you see how remarkable quantum gravity will be. You see that we have g, Newton's constant, which is characterizing gravitation. We have c, the speed of light, which is characterizing special relativity in the relativistic aspect. We have h bar, quantum mechanics. But even you can restore k, and you see that this is a statistical thermal formula as well. And for me, my greatest love is geometry, and you see that the area of the horizon enters this formula too. So if we're able to quantize gravity, we're going to have a remarkable unification of all of the different areas of physics that enter this formula. And I think it's a really good framing for thinking about both the excitement of quantum gravity and the challenges that we're going to have to face. So I'm going to take things in 3 parts. I'll try to take a break in the middle for a big set of questions and for you just to catch your breath. But the first part is going to be all about subsystems, gluing, symmetries, and constraints, trying to understand how we break up the quantum gravity into pieces. The second part, I want to tell you about some recent work on quantization and tunneling, and the fact that discreteness and tunneling are actually connected to each other in a subtle and interesting way. Anything I can help with?
Oops, sorry.
That's a bad idea. No problem.
Yeah, if you can share when you share the slides, make sure that you share the content on your screen.
Did I lose the meeting?
Yeah, so the slide you went on didn't keep updating as you changed slides on the Zoom meeting.
Okay.
So go to the Zoom meeting page.
Zoom meeting. Back to meeting. Thank you. That doesn't seem to work.
So stop sharing and let's restart. Let's share. Share again. Not the keynote, but the desktop.
Sorry?
Share the desktop, so that way whatever is on your screen is being shared. Okay. Yeah. Thank you.
No problem.
Can you do it first? Yeah, perfect.
It's working? Wonderful. They said it was, yeah. Okay. I'm the test case that we work out all the bumps with. And then finally, I want to talk a little bit about this thermostatistical aspect of gravity and try to connect a little bit to gravitational phenomenology. Of course, this is very much an area in development. All right, so let me begin. As I said, I want to take the simplest possible case. So let's consider a static weak field so that general relativity reduces to Newtonian gravity. In this limit, there's a remarkable analogy between gravitation and electromagnetism. Each of the identities that you're familiar with from electromagnetism has an analog in gravity. So let's introduce the weak field potential. You can see it in the metric there, and the gravitational field as its gradient. Then we have a gravitational Gauss law that states that the divergence of that gravitational field is equal to the mass density. And in particular, just as in E&M, this is a place where a very interesting non-locality sneaks into the theory. The gravitational Gauss law can be expressed as the flux through a surface. So this flux encodes the total mass contained in that region. And this is going to be our main focus for this first part of the talk. This encodes a surprising amount of information. Let's go even further and consider a region where we have a small enough Gaussian surface that we can take the gravitational field to be constant so that it pulls out of this integral. And since I've oriented both the surface and that gravitational field arbitrarily, well, if the region is empty of mass, then this dot product is just encoding the fact that the closed surface integral of the area of the plaquettes of that surface is equal to 0. So a constraint in the weak static field with a massless region is that the total area over a surface is 0. Penrose has a beautiful way of thinking about this. If I imagine the solid surface, immersed it in water, the total pressure would be zero, but the pressure is just proportional to the area. So this is a way of thinking about this gravitational Gauss law. We have to be careful. There are three important subtleties when you think about this expression. So the first subtlety is that it's very tempting when you come from a non-relativistic stance, when you learn physics from the ground up. It's very tempting to think of that area as just expressed in terms of the coordinates. You coordinatize the vertices of the tetrahedron, and you just talk about the lengths as different coordinate differences. But of course, the whole point of general relativity is that the gravitational field is what determines the actual geometrical extent of surfaces. So even though we've written this as an integral that directly is expressed in terms of areas, those areas have to be computed through the metric. And the coordinates are just arbitrary labels that keep track of the pieces of our surface. So on the one hand, you can write that in terms of the traditional metric that you're familiar with, but Astrophysical really wanted to think about this more deeply as a gauge theory, and introduced a triad field, a three-dimensional frame field in your 3D hypersurface called capital E, and you can see the expression for it here. And there's a lovely early paper of Carlo's where he shows that you can rewrite this area directly in terms of that frame field. It's just the integration of that gravitational electric field over the surface. All right, so the first subtlety is not to conflate the geometry encoded in the field with the coordinates. A second beautiful subtlety is this insight of Reggie's, that if we work with a discretization of our space-time, we can use the direct metrical variables as the variables of our discretization. So we can use the length of edges as our variables, or we can use the areas of faces as our variables. And when we do this, we can directly work in terms of relations between the geometrical quantities. So this is another advantage of the discretization. It frees us from thinking about coordinate quantities. Here, I'm writing things in terms of the cross product, but of course, the cross product is a three-dimensional thing. It's special to 3D. And we saw in the previous slide that the wedge product, the E field, was actually written in terms of the wedge product. And this wedge product is a more natural character to think of living on these two-dimensional surfaces. But you probably know that the wedge product encodes an SO3 Lie algebra. It encodes directly the symmetries of an angular momentum vector. So by building areas up out of this gravitational electric field, you're thinking about a symmetry that has an angular momentum structure, an SO3 structure. So this SO3 structure is an important piece of the story that we're going to build up on from now on. And we can always think of going back and forth between the wedge of two edge variables to get an area, or the cross product as long as we work in 3D. So if I decide to think about a three-dimensional slice, I decide to discretize down to a single piece of that slice, and I think of our gravitational Gauss law, it becomes just that the sum of the area vectors of each of the faces of the tetrahedron is 0. So these area vectors are vectors that point normal to the faces and whose magnitudes are equal to the area of that face. But now we can interpret this gravitational Gauss law directly. It's explicitly expressing the fact that the geometrical shape of our tetrahedron is invariant under rotations. This gravitational Gauss law has a second characterization. It's not just expressing closure, but it's also generating the transformations that leave the shape invariant. It's generating rotations of our shape. So this is a beautiful way of thinking of this Gauss law, and it's also directly related to thinking about bivectors. The exponential of a bivector generates rotations. Okay, so with this as our setting, we now are ready to start quantizing our geometry. And I wanted to emphasize these symmetry aspects because the quantization draws on them very directly. As soon as we decide to think about these areas as angular momenta, We know immediately what their Poisson structure is, the very familiar Poisson algebra SO3. We can write the Poisson bracket of any two functions on our phase space. And furthermore, we know directly how to quantize them, because angular momentum operators have a very familiar JM basis that we can work with, a Hilbert space that we know and know how to quantize. So the identification of an area with an angular momentum immediately leads to an area spectrum. The area spectrum acting on a spin j is the square root of j times j plus 1. Here, the AP is the Planck area, the sort of fundamental unit of area on our surface, and gamma is a Barbero-Mirti parameter, which characterizes the spacing between our area eigenvalues, the area gap, if you like. So now we have a spectrum associated with each of the faces or the facets of our tetrahedron. We can ask if there's more quantum geometry. Can we do more than that? And indeed you can. It's a surprising but elementary fact that the volume squared of our tetrahedron is expressible in terms of the triple product of area vectors. If you want to derive this for yourself, it's not hard at all. You just start with the usual formula that the volume of a tetrahedron is 1/6 the triple product of the edge length vectors, and you re-express the areas in terms of those edge length vectors, and you'll be able to find this formula directly. Lots of hard work in the 90s led to a loop quantization of this volume operator, now seen on the Hilbert space as this collection of four angular momenta. And that volume operator has a discrete spectrum as well as the area vectors themselves. So on the right here, it's a little bit faded on the screen, but you can see these open circles. Those are the spectral values of the volume, where I've, just for plotting convenience, connected the areas of the four faces of our tetrahedron so that they're all expressed in terms of a single spin parameter. So this allows us to say what a spin network is. A spin network is a collection of fuzzy quantum tetrahedra or quantum grains of space. They're quantum both because we found that they have discrete spectra, but you may notice that if you wanted to completely specify the geometry of a tetrahedron, that geometry would need all 6 of its edge lengths specified, right? And here, what have we done? We've only specified the 4 areas and the total volume of the region. So there's a parameter in the shape of this tetrahedron that's free. And that parameter, we can spread it out smoothly over its whole set of allowed values, and that's like our quantum state. So a single grain of space can be described by 4 spins, the areas of each of its faces, and a single intertwiner, a single thing that connects those, which is the volume. And that gives us a complete set of commuting observables that determine our spin network state. If we then imagine specifying a particular graph with a particular connectivity, we can specify those spin network states at each of the nodes of the graph, and we can mod out by this overall rotation that we were investigating, and we obtain the Hilbert space on the right here, L2 of SU2 to the number of links at a node divided by the gauge transformations at each node. So this is quite a striking picture of the geometry of spacetime if you've never met it before. It's a picture where there is no background on which the metric or the geometry of spacetime lives. The quantization of these grains is creating the space itself. Okay, so I'm going to interweave the narrative that I'm trying to tell you about the geometry of spacetime, about the quantization of spacetime, with ideas and challenges from the quantum gravity community, ideas that I hope you all will be feeding back into and helping us to think about. So the first great challenge that I see in quantum gravity is an error that gets made again and again and again in papers on quantum gravity, which is to too easily make this split, the subsystem split. To imagine that you can take your Hilbert space and break it into a tensor product of two Hilbert spaces. The reason that this can be such a problem is that if you don't impose constraints like this Gauss law constraint, that split just isn't valid. And it gets worse when you get into the full symmetry of the theory where you have diffeomorphism constraints as well as the Gauss constraint. So the right way to think about it to achieve space-time subsystems is one of the big problems that I'd like to understand much more deeply. In fact, it could be that we even need to generalize the notion of tensor product. So in the classical system, often when you glue two classical dynamical systems, it's okay to identify their degrees of freedom, but then you have to symplectically reduce by the variable that you've identified. And that symplectic reduction is actually what gives you the gluing. And it may be that we need something like that as a tensor product, something that allows for fusion of the degrees of freedom after you've identified them. So this is exciting work that's been investigated by, for example, William Donnelly and Laurent Friedel, and on the quantum information side, Pablo Arrighi and company. And this is a big thing that I think we should really keep thinking about. Wonderfully, in a spin network, people have been able to understand how you put fermions on this spin network lattice. But I'd like to be able to see things go a little bit further here. I'd like to better understand how the matter interacts with this gravitational Gauss law that we just described. Indeed, you can see on the bottom of the slide here, when we have the gravitational Gauss law with a degree of freedom of matter on our spin network, we should get the mass encoded on the boundary also. That mass encoding on the boundary means that maybe even it's going to be a good idea to adjust our kinematical Hilbert space. So we started with grains that just describe the boundary geometry, but perhaps we also need to think about the total charge, the total gravitational charge contained in the region, and adjust the kinematical structure to encode that mass that we contained in the region. The analogy I have in mind here is, of course, electromagnetism, where if you want to glue, say, the interior of a ball that contains a charge with the exterior of that ball, you have to encode the total charge inside that ball on the boundary in order to make that gluing. So, so this, for me, has a really interesting exposure of the interplay between matter degrees of freedom and gravitational degrees of freedom that's very characteristic of gauge theories. Riello and Gomez have called this the co-rotation principle. We know that you can rotate the fermion field with a gauge transformation, and you have to correspondingly rotate the gauge field with that gauge transformation. So I'm interested in better understanding co-rotation in the context of gravitation. This is my understanding of what the people who work on edge modes and corners and corner symmetries and really are thinking deeply about the nature of gauge theories with boundary. This is, for me, what they're trying to uncover, is a better way to understand the kinematics of how we gauge when we have charges in our regions. So this is something I'd like to understand better. Perhaps an example of this comes when you generalize the flat Euclidean tetrahedron that I was just looking at to the case where you have a cosmological constant, And that cosmological constant, it acts to make the geometry constantly curved. So you have to indeed generalize the Gauss law in that context. And you have to work instead of with the SO3 Lie algebra elements, the vectors, the angular momentum vectors themselves. You have to work with SO3 group elements. You have to generalize to the exponential of those Lie algebra elements. That generalization leads to a more complicated encoding of your gauge transformations and of your Gauss law. It becomes a group product that's equal to the identity. So from my mind, this is an example of how you might actually start to see the encoding of the charge on the boundary. There's another intriguing connection here that is very much just suggestive, and I'd be very interested to hear people's thoughts on it. But if you try to quantize that more complicated geometry, the constant curvature geometry, what you encounter is the whole technology of R matrices and Q deformation. And that quantization has a very similar character to spin statistics. The group elements are not commutative, and you have to think about how they fail to commute when you describe the geometry. And that Q deformation can actually bring in an additional phase factor when you exchange pieces of the geometry. But this starts to make a really interesting connection between spin statistics, again, between matter degrees of freedom and geometrical degrees of freedom. All right, that's my first set of challenges that I'm posing to all of you. I'm hoping by the end of the meeting you've solved all of them and can tell me what's going on. In the second part of the talk, I'd like to tell you about a piece of traditional quantum mechanics, standard quantum mechanics, but that ends up feeding into the description of gravity in a way that I find very intriguing and that I'd also like to leave the meeting with a deeper understanding of. So I'm going to tell this whole story in the semi-classical context, so I'll be working at lowest order in Planck's constant. This is really because it's the place where I think I'm most familiar with what I'm going to be telling you. However, I want you to know from the outset that everything I'm going to say actually has a generalization to all orders in H-bar, and I'll try to hint at that a little bit as we go on. Much has been written about the fact that quantum mechanics is somehow intrinsically complex. You need complex numbers in order to study quantum mechanics. The quantum information folks have really tried to pull this apart and understand it more deeply, and there were even announcements in the APS news this last few months about experimental tests that confirm that somehow complex numbers are intrinsic to quantum mechanics. Something that I think people are much less familiar with is the fact that classical mechanics also has a lot of structure when you complexify it, and that structure actually tells you about the semi-classical aspects of quantum mechanics. So to better situate the ideas, I'm going to start with a very familiar example, and I'm going to describe everything in terms of that example, and then I'm going to try to reconnect with quantum gravity. So the example that I had in mind is just a chordic oscillator, an oscillator with a double well, and just for simplicity, I'm going to take the symmetric case, but nothing I'm about to say is restricted to that case. In the classical theory of the motion in this well, you might select an energy for your classical particle. Say I select the energy E drawn here, and I put my particle in the left well. Well, then the particle will just bounce back and forth in that well. So we can describe that by the conservation of energy, just the sum of its kinetic and potential energies. Here I've made explicit what the potential energy is. And you can solve that conserved energy equation for the momentum of the particle anywhere in the well. There's interesting branching at the turning points, the places where the total energy is equal to the potential energy. Those are the places where momentum goes to zero, and that's how momentum can switch signs and we can bounce off the wall of our potential. But I want to go deeper into classical mechanics and understand the sort of action aspect of this problem. So let's introduce the action integral. It's just the integral of P to Q. We know P is a function of Q from the middle of the slide. And we can carry out that integral from one turning point to the other and back, and we get a closed integral. I don't know, many of you may know, Einstein in 1917 was the one who appreciated that P to Q was the right thing to work with. In fact, sum of P to Q in the phase space of many degrees of freedom. The appreciation was an appreciation of symplectic coordinate invariance. There's a very deep insight in that paper. He's the first one to introduce quantum chaos, in fact. But I'm not going to go there right now. So we get this action integral, and there's a second piece of classical mechanics that's immediately tied into that. You can take the derivative of that action integral with respect to energy. If you just carry that derivative inside the integral, you see that you can get basically 1 over p. In fact, it's m over p, but that's just 1 over the velocity, and this is exactly encoding the period of the motion. So here's the traditional classical mechanics of this oscillator. I want to do complex classical mechanics. So I'm going to complexify my position variables. In fact, if you like, I'm going to complexify every variable in sight. And I'm going to study what I get when that happens. Well, we already noticed that the turning points are branch points for the momentum. The square root function branches at those points. So if I complexify my variables on the left, you see that I have to make branch cuts. The little a, b, c, and d are my branch cuts that allow me to define what I mean by momentum when I pass through one of those cuts. In fact, I need 2 branches because I have a plus or minus for my square root function, and that's the 2 copies, the positive momentum and the negative momentum. If you carefully track those branch cuts, you can glue those 2 sheets of momenta, and you get the surface that I'm showing in the middle. And the remarkable insight that comes from doing this is that the topology of that surface is non-trivial. If you like, because we're working in complex variables, what everybody always does is wrap the momentum plane, the complex Q plane into a Riemann sphere. So if I did that, I would actually get 2 copies of the Riemann sphere. I make my same branch cuts, and when I glue, you see that I get a torus. So this is describing the topology of the complexified classical phase space. That topology highlights the fact that there are actually 2 cycles along which I can integrate my action, my symplectic potential, my PDQ. There's the cycle that runs around the A and B branch cut. That's the black cycle. I've called it alpha, and you can see it on the torus as well. But now that I've copied both branches of my momentum, you see that I can run from between the 2 inner turning points. I can go down to the other momentum sheet and come back up to the first momentum sheet. That gives the red beta cycle. And let's introduce the action integral along that red beta cycle. We'll call it the dual action. So we have the usual action you're familiar with from classical mechanics, and now we have a dual action. Topology and complex analysis, the Cauchy integral formula sort of things, tell us that these are the only 2 non-trivial closed cycle integrals on this surface. Intriguingly, both of these are encoding aspects of the quantum mechanics of the system. You probably remember in old quantum theory, you can do a Bohr-Sommerfeld quantization using the regular action. Bohr-Sommerfeld quantization says that I should set the action equal to n plus a half times Planck's constant. The action is expressed in terms of the given energy of my system. I can invert that equation and I get the energy levels. So I would get the discrete energy levels of my quartic oscillator. But it turns out, and you know this already, if I have the yellow energy, the 2 wells are degenerate. So there's 2 separate states that have the same quantum energy. But that degeneracy is in fact broken by tunneling. You can imagine if I started with a wave packet in the left well, over time it would tunnel into the right well. And in fact, the energy states are symmetric and anti-symmetric combinations of the states in the 2 wells, and those 2 initially degenerate states actually get a splitting due to tunneling. That splitting is exponentially small. It's called delta E. It's exponentially small, and you can write it directly in terms of that dual action that I just was showing you. So the dual action is encoding aspects of the tunneling. If you like, the complexification is allowing for the openness of the quantum system, the sharing of our wave packet from the left well with the right well. Okay, This is very mathy. I just want to take you through it quickly, but don't feel like you have to follow every step here. What I want to tell you is that the story I just told you about the quartic oscillator is in fact very general. It works for all sorts of 1D potentials. The way to see that is that when we complexify, we're always going to get branch points at the turning points of the classical system. We can always do this Riemann sheet doubling and glue the whole thing into a Riemann surface. And that Riemann surface will have some genus G. Perhaps your classical mechanical system also comes with some special structure that makes points of the phase space special. If so, maybe you have punctures. And from algebraic topology, we learned something really interesting. The number of independent cycles on our genus G surface and the number of holomorphic one forms on that surface are directly related to each other. In fact, they span a finite dimensional vector space, and that vector space has a dimension of 2 times the genus plus 2 times the number of punctures minus 1. But we can repeat the whole strategy we just used. Notice how we got the dual action. We took our symplectic potential, we took an energy derivative of it, and we got another one form on the phase space. We could repeat that, take another energy derivative, take another energy derivative. We're going to get independent one forms, but we know the space is finite dimensional, so at some point we're going to run out of independent one forms. And there's going to be a linear dependence amongst those one forms, or up to a complete derivative. So that's the df on the bottom there. If we now integrate that linear dependence amongst our one forms, well, the closed form that they're equal to integrates to 0 on a closed cycle. And we learn that there's a direct differential equation that relates the actions along independent cycles. This differential equation, which I've drawn schematically on the bottom right, is called the Picard-Fuchs equation. So that became very abstract, so let me ground it in the quartic oscillator again. Here at the top of the slide, you see the Picard-Fuchs equation for the quartic oscillator. Notice the logic here. What we're doing is we're studying our classical mechanical system as we vary the energy. We're trying to understand the structure of our potential as the energy goes above the barrier, say. That sort of thing. The Picard-Fuchs equation is almost like a dispersion relation, right? A is P dq, but we took energy derivatives. It's like we're extracting the action version of a dispersion relation. And every action on this genus G surface is going to be related by that Picard-Fuchs equation. They're all solutions to that Picard-Fuchs equation. So what this means is that the action and the dual action aren't even independent of one another. You get a Wronskian condition from our differential equation that directly relates the quantization, the Bohr-Sommerfeld quantization of levels, to the tunneling between those levels. It's a perturbative, non-perturbative relation. It's a very interesting structure buried in the quantum mechanics. In fact, the complexification of the classical mechanics. So on the bottom left, you see what this amounts to for the quartic oscillator. It amounts to a very simple condition that relates the action and the period, and the dual action and the dual period. And they will, at every energy, they'll satisfy that. So this frames a new way of looking at a quantum mechanical system. Don't look at just one energy level, but study the family of energy levels. That's the idea of Picard and Fuchs. This is quite powerful. It turns out that these Picard-Fuchs equations allow us to express all orders in h-bar quantization. If you can do perturbative quantization up to some order in h-bar, you can also understand the non-perturbative tunneling to that same order in h-bars. And there's always a relationship between the two. So I'm not going to go into the proof of that here, but I think it's a remarkable fact. So why am I telling you this story from quantum mechanics? Well, on the one hand, I just think it's beautiful and fascinating. we found a sort of Kramers-Koenig relation for quantum mechanics, a relationship between the allowed energies and the dispersion of those energies into other wells. And strikingly, the exact same logic applies to our quantum grain of space. You can start to understand what's going on with tunneling of quantum grains of space in this way. So recall that we had the closure relation of our area vectors. This was our gravitational Gauss law, and it had a symmetry algebra. It was the SO3 symmetry algebra. Let's take those area vectors. We know they have to sum up to 0, and let's rearrange them so that they're end-to-end in space. And let's introduce the diagonal. The reason for doing this is that the tetrahedra that have fixed magnitudes for their areas becomes a spherical phase space. You can see this as follows. We're describing sets of 4 vectors that close up to 0 in R3, but sets of 4 vectors with fixed magnitudes that close up, you can bend them around their diagonal, and that gives you one variable, the angle, or you can deform them so that they become more of a diamond shape and less of a diamond shape, more of a square, more of a diamond. So our 2 phase space variables are the angle between the wings and the length of the diagonal of the wings. And that gives us a sphere. The topology of that phase space is a sphere. It's quite beautiful. So what am I saying? To every point on that sphere corresponds a tetrahedron with fixed phase areas, and vice versa. Now we have a symplectic structure on our sphere, and we can repeat the whole story I just told you for the quartic oscillator. We can fix the volume, and we get contours of constant volume on that sphere. Then we can integrate PdQ, the angle and diagonal of our tetrahedron. We can integrate it along one of these closed volume contours. By doing that, we can impose that equals an integer multiple of Planck's constant, and we can find discrete values for the volume eigenvalues of the tetrahedron with fixed phase areas. We can find the spectrum of our spin network grains of space. This is work that Eugenio Bianchi and I did some years ago. The dynamical system that emerges from this volume evolution is quite striking. Lambda is the parameter along the volume evolution, and we find a sort of momentum like we were looking at before. The diagonal, the derivative of the diagonal with respect to this volume parameter is a coordinate, square root of a coordinate. The Bohr-Sommerfeld quantization, I wanted to show you the dynamics. This is why we fought with my computer to do this. You can see here the actual dynamical evolution of a tetrahedron along one of these volume contours. So what this video is showing you is a tetrahedron that has fixed phase areas and fixed volume, but is changing shape. It's that freedom that we notice. The complete set of commuting observables doesn't completely determine the shape. So instead, you can watch the shape evolve as you move along the volume contour. The 2 tetrahedra are just 2 different perspectives, because it's hard to see what's happening from one perspective. So they're just the 2 halves of the video are just showing you different pieces, different views of the same tetrahedron. So the Bohr-Sommerfeld quantization that I just mentioned is an extraordinarily good agreement with the loop quantization that I mentioned at the beginning. You remember the loop quantization with the open empty circles. The Bohr-Sommerfeld quantization here for the exact same eigenvalues is shown in black dots, and you can see the discrete spectrum of the volume agrees perfectly between the 2. Perfectly, I'm exaggerating a little, it's not quite perfect. On the rightmost row, you can see that they're a little shifted off center, but that's to be expected. We're working at first order in each bar here. Okay, but the thing that I think is so fascinating is that we can go further. Semi-classical quantization also allows you to build wave functions. So here we have an explicit wave function. I've only solved for the wave function in the classically allowed region of volumes, and so that's why you see these run off at caustics, but you can solve for it in the classically forbidden region too, and it agrees very well with the points that fall off as you emerge away from a Euclidean tetrahedron. But that's interesting. What does it mean to emerge away from a Euclidean tetrahedron? Well, I said that we had a square root of a quarter. And if you take the volume equals 0, you get this blue curve that I'm showing on the right. So Q was the volume squared. If I take that equal to 0, I get the blue curve. On the other hand, if I turn on the volume, I get the yellow curve, and it intersects. And I have exactly the same sort of situation as we had for a quartic oscillator. I have a volume that determines 4 roots. Those 4 roots act as branch points for my volume evolution. I can complexify those the space of states and look at the branch cuts that result. And we get exactly the same sort of geometry that I mentioned for the quartic oscillator. We get a genus 1 torus that comes from gluing together the complex phase space of our tetrahedron. But what is this complexification? Well, it turns out you get a Picard-Fuchs equation just like you did before. Just as we were imagining varying the energy in our potential, we can imagine varying the volume and tilting this curve. That leads to a Picard-Fuchs equation that I show at the top here. I'm showing it schematically because this is what it actually looks like. So I won't go into more detail on that. But you find incredible relations between the actions in each of the segments between the roots. These are non-perturbative formulas that tell you the modular connection between one action and the other. Completely explicit formulas that you can write in terms of elliptic integrals. So what are we finding? We're finding that if I start with a Euclidean tetrahedron with fixed phase areas and fixed volume, that necessarily the spectral discreteness tells me that that can tunnel. And you can actually solve what it tunnels to, and it tunnels to a Lorentzian tetrahedron with the same phase areas and the same volume as magnitudes. It's not a coincidence that you may have noticed everywhere areas were showing up squared and volumes were showing up squared. That's because we can use the same trick that we use in the metric. When you work with the squared variables, the sign in front tells you the signature, tells you whether I'm dealing with space-like or time-like things. The exact same thing happens here, and you get a geometry on the right that is Lorentzian. This is quite striking. If I fix the geometry of a grain of space, it's totally fine and possible for it to tunnel, at least as a dynamical system, for it to tunnel into a Lorentzian geometry. And so we're actually going quantum mechanically between different signatures of space, of our geometry. So I think the direct quantization of geometry provides a remarkable laboratory for understanding this resurgent perturbative, non-perturbative relations. There's a much, much broader theory behind this that works in terms of path integrals in general. It's called resurgence. And there's a whole community that's trying to understand resurgence in quantum field theory, and I'm hoping to introduce it into quantum gravity. All right. This leads to a whole host of challenges and striking ideas that litter quantum gravity, and that, again, I'm hoping you all will inform me about. So let me go through these. I'm going to take these a little bit slower than I took the first set of challenges. I think it's a remarkable idea that we actually have a connection between Lorentzian and Euclidean geometry here. It goes back to an old idea of Carlo Rovelli and Simone Speziale. How are we going to get our discrete space-time to respect Lorentzian variance? The idea is that the symmetry should be implemented in the same way that it's implemented in the rotations of, say, an angular momentum. We know that with one orientation, our angular momentum has a discrete spectrum along the z-coordinate, for example. But then when I rotate, the covariance of the theory says that the state goes into a superposition of states that are still discrete, but respect the spectral properties of the two. I think now we have the opportunity to investigate these same sort of ideas in the geometry of space-time. The proposal has long been there that when you boost a tetrahedron, it should do that same spectral mixing, and that's how we maintain the discreteness of space-time. But I think we may be able to tackle that problem concretely now, and I'd love to see it worked out in an example completely explicitly. The introduction of space-time into the discussion, rather than just thinking about space, means that we also have to face the fact that if I'm going to work with area variables, if I'm going to work with a slice of space, in fact, there are two normals to that slice. There's a spatial normal to that area, and there's a time-like normal to that area. And one of the ideas that's been key in loop quantum gravity is to say that if this is to be a well-defined area, if I'm really going to talk about a geometry of a piece of area, well, those two normals have to agree with each other. So the spatial normal should be related somehow to rotations, to the angular momentum algebra that we've been talking about. But the time-like normal should be related to boosts. And if those two are to agree, then we're going to need that their generators are proportional to each other. That the generator of boost k is related to the generator of spatial rotations. So this is a way of understanding the linear simplicity constraint that's been introduced into role in the two most common spin foam formalisms, the PRL FK model. What do these constraints do? A way to think about them is that they take a topological theory, a theory called VF theory, and they impose constraints on that theory that make it into gravity. And those constraints are exactly this thing that we just said. The areas are well defined when you view them from both normals. The interesting and surprising fact is that if you look at this constraint carefully, you'll find that you can't impose it strongly. If you impose this constraint strongly, that is, you require all states to satisfy it exactly, then you are going to kill the curvature of your spacetime. In the discrete context of area Reggie calculus that I started the talk with, you can see this as the equations of motion of area Reggie calculus giving zero curvature. But we know what what to do about that issue. We don't impose this constraint strongly. Instead, we impose it weakly. That is, we impose it as an expectation value. But imposing it as an expectation value allows you to see that the salad points move off into the complex plane. And that connects really interestingly with the complexification that I was just introducing you to. So the weak implementation of these constraints that we've recently found an effective formalism for this, and that effective formalism is bringing numerical calculations into the realm of possibility that weren't before. And we can see that the spin foams actually, when you weakly impose this linear simplicity constraint, give good dynamics to your spin foam geometries. The full theory has also been put together in a formidable numerical code that I'm extremely impressed by. It implements the full spin foam as a C code that's been fully parallelized and used every trick in the book in order to make it computable. And this is a remarkable work of Flitzini and collaborators. I think that the tunneling of geometry illustrates that we're going to have to think about a lot of issues very carefully. Issues of causal structure and quantum causal inference. So Rob Speckens was hoping to be here this morning, but unfortunately was sick. Rob Speckens has been thinking about Bayesian causal inference. How do I build up, as part of my theory, the causal implications, the arrows that connect causality? And I think this fact that we can go from from a Euclidean signature tetrahedron to a Lorentzian one means we're going to have to think very carefully about the kind of inferences we make on causal structure. In the spin foam formalism, Bianchi and Martin Dussard recently introduced a way to keep track of the signs that you assign to your branes of spacetime, and which respects causal structure. So this is a really interesting place to start to understand these dynamics. a number of people, and I only selected 2 references here, I meant to put a dot by dot, a number of people have been thinking about the end of black holes. And interestingly, also at the end of black hole evolution, there are several causal issues that emerge, and the different causal issues are separated from one from another. There's an issue around what we've called the A region in this picture. So in the A region, you're near the Schwarzschild singularity, and you have to understand how that Schwarzschild singularity is resolved by quantum gravity and evolves into the future. So one proposal is that it evolves through a white hole transition, a time-reversed version of the black hole. But there's a separate causal issue. There's the issue of where the horizon meets your spatial evolution. This is the late time region, the B region, where you're very late in the evolution of this black hole, and it's not clear how the singularity structure comes and meets the exterior. And then there's the deep core of the black hole, where presumably the matter that formed the black hole goes, and you have to understand the causal transition of that matter. There's matter degrees of freedom as well. So I think there's a whole host of interesting questions there. A final issue that I again, hope that you all will teach me about is a question of whether topology change is essential to quantum gravity or whether it's sort of an oddity that's sitting on the side. In cosmology, there's a fascinating proposal, the Hartle-Hawking proposal for the evolution of the universe, which is that topology change allows a Euclidean signature spacetime to emerge from nothing and then to evolve into a Lorentzian signature spacetime. This is very much in line with this sort of evolution of causal structure that I was just mentioning, but it's complicated, and the causal structure, when the topology changes, is extremely complicated. It's very singular there. Our formalism allows for, by working in these triad variables, we allow for causal structures that are singular at points, and allows for topology change, but is it physically essential or not? All right, I've been talking for some time. I want to take a pause. I do want to go into quantum gravity phenomenology. It'll be the last part of the talk, but I'd love to pause, let you stretch your legs and ask some questions if you have any. All right. If there aren't any questions now, I'll continue on, but don't hesitate to interrupt me. With all the technical details at the beginning, I forgot to say that. I'm going to invert the logic in this last section. I'm going to tell you some of the challenges at the outset, some of the puzzles that I'd like to understand better, and then I'm just going to go into one very specific example. The example is selected because it's something I've thought a lot about and I'm very interested in, but there are many more avenues for thinking about quantum gravity phenomenology. So one of the quantum gravitors that's part of the QISS collaboration is Robert Urkel, and he was the one who initially emphasized that we should think about finite space-time regions. We should take the evolution of one spatial slice into another spatial slice, specify the metric all around the boundary of that, and think about the spin foam evolution that fills in that boundary geometry. This general boundary formalism has been fascinating for quantum gravity, but it leads to something very, very interesting. If I'm going to focus on a finite region of space-time, I'm going to have to trace out the exterior of that finite region. And by tracing out the exterior, I'm naturally going to arrive in a non-pure state. And so we start to see that thermodynamics sneaks in even in our setup of quantum gravity. There's statistical ignorance about the exterior of the region. Indeed, one of the first examples of this, it wasn't done this way first, but a first example of this is the Unruh effect. When I think of an observer who's moving at a constant acceleration, they're stuck in one wedge of Minkowski space. And that means they're tracing out the exterior of that, and that's a way to understand the thermality of the detectors that the Unruh observer sees. So quantum gravity blurs this boundary between between quantum mechanics and thermodynamics in a way that's very interesting, and which has been built even into a formulation of a completely thermodynamical formulation of the Einstein equations. Many of you have thought very deeply about entanglement, and Bianchi and Myers promoted this sort of thinking into a question about whether this is actually the architecture of space-time. That when you trace over its stereo regions, you naturally sort of get an entanglement entropy that's like the Bekenstein-Hawking entropy on the boundary of your space-time region. So this is an interesting problem for us to exchange and collaborate around. Okay, as promised, I'm going to zoom down and just think about one phenomenological piece. That phenomenological piece is going to try to address the fact that black holes seem to have this very bizarre dual nature. On the one hand, as solutions of classical general relativity, they're completely characterized by their mass and their angular momentum. So they're somehow the simplest objects in nature. On the other hand, the Bekenstein-Hawking entropy says that associated with this black hole is a huge entropy, absolutely ginormous entropy given by horizon area in Planck units. And so how can we square these two perspectives on the black hole? Well, gravitational thermodynamics has some very unusual and surprising aspects to it. Because gravity is long range and cannot be shielded, somehow it's very difficult to isolate gravitational systems. This is what I was saying at the beginning. The constraints don't allow us to easily do subsystem decomposition. But that means that a lot of the standard thermodynamics that we're used to, the fact that when I take a system and I double it, the energy doubles, the energy is extensive. Well, the nonlinearity of gravity undermines that. If I double a system, the two pieces start to interact, and it's very difficult to describe what the energy of the interacting system is. So both of these facts undermine the basic notion of thermodynamic extensivity and much of the usual formalism. On the other hand, from my perspective, one of the most promising avenues into understanding of quantum gravity phenomenology is going to come from thinking about thermostatistical arguments. Blackbody radiation, it's not a coincidence that was the first place we got access to quantum mechanics in some sense. And so I think it's really interesting to think about gravitational thermodynamics. So let's illustrate this concretely in a simple example. Here I'm borrowing from one of our philosopher collaborators in the network, David Wallace. So just think of a self-gravitating gas. Well, because it's self-gravitating, it has some unusual properties. The virial theorem says that the potential energy and kinetic energy of this self-gravitating gas are not independent of each other. In fact, the potential energy is given by minus twice the kinetic energy. So if you add them up, then the total energy is negative the kinetic energy. And this is very odd behavior because if I now use equipartition, I can explicitly compute the heat capacity, and we find that this self-gravitating gas has a negative heat capacity. So what that means is that the self-gravitating gas tends to want to give energy up to its environment. And it's very strange and hard to understand exactly how this large entropy of a black hole results. You take your self-gravitating gas, and if it condenses, it cools. And it seems that its entropy should go down. It does go down if you compute it. So how do we understand what's happening? Well, it turns out that you shouldn't really think of the gas as a homogeneous substance. Instead, you should think of it as sort of a core and shell, or a core and a halo, people often call it. So you can give up energy from the core. It does indeed cool and reduce its entropy, but it gives energy to the halo around it. And that halo heats and gains entropy. So the overall system evolves as it should, but in a rich way. And so it's quite interesting how the instability of gravity actually turns this into a highly entropic system. The instability of gravity can allow, if you put enough mass, for the core to capture its own halo. And as it captures its own halo and the radiation that being emitted in that halo, that's when it raises entropy very high. The core is not carrying all the entropy. So it's a very rich interaction between these two. This is the paper that Wallace put out, but it's also been understood and thought about very carefully by relativists, for example, Pretorius Bullock in Israel. So is collapse even avoidable? Well, we all know that Penrose won the Nobel Prize recently for showing that collapse is generically not avoidable. But it's very interesting how it comes about. Only if you have a spherical distribution of matter do you get a spherical collapse. In general, if you have perturbations, if your system's richer, as you collapse, your black hole is going to start to spin. And Penrose is a remarkable artist. If you've never appreciated his drawings before, I find this gives you an intuitive sense of that spin up during collapse. Well, as part of that process, the system is going to let off gravitational radiation, and you all know the story that this has been a huge impetus for research in the last 10 years, longer. So here's the initial catalog from the first run of LIGO. The purple dots you know are electromagnetic black holes. These are X-ray binaries primarily, where one star of a binary pair has collapsed to a black hole, and you're seeing the accretion off the other star. And the blue ones are the LIGO black holes measured in gravitational waves. So let's try to describe a black hole thermodynamically. If we're going to describe it thermodynamically, we have to set up a thermodynamic ensemble in which to think about it. So let's take a black hole, isolate it very well, and imagine that we're in an asymptotically flat space-time and we can contain the total energy of that black hole. We'll call this the microcanonical ensemble. Something very interesting comes out of this ensemble. If you look at the Bekenstein-Hawking entropy, that entropy, of course, depends on the spin of your black hole. But you may not have ever looked at that in detail. As I've introduced here the Kerr parameter, the angular momentum divided by the appropriate units to give you a dimensionless measure, the Kerr parameter. If you look at the black hole entropy as a function of the Kerr parameter, the black hole entropy actually decreases as you increase the spin. But then if we imagine that a black hole formed in this ensemble, formed microcanonically, this means that black holes with large spins should be highly, highly improbable. They're way less entropic. And so here we've done a contour plot for different masses of the black hole, going from 2 Planck masses to 2 micrograms up towards 20. And you see that as the mass of the black hole increases, this distribution becomes highly, highly peaked near zero spin. You can make this quantitative, and the micro black hole should have a spin, dimensionless spin parameter of order 10 to the negative 38. So remarkably small spin. Can we form black holes according to the microcanonical ensemble? Is that possible? The idea that we've been proposing and thinking about, and I find quite fascinating, is to kind of model our understanding of cosmic microwave background radiation and see if we can do something similar with black holes. So inflationary models provide an incredible explanation for this CMB. Thermal fluctuations aren't enough. They're too small to explain the temperature anisotropies of the CMB. But these anisotropies are well described by Gaussian statistics of quantum curvature perturbations. So what if there were large perturbations? What if we could study the result of a large perturbation in the early universe? Well, you can just do that according to the microcanonical statistics that I just mentioned, and you get this equation here. The probability of a particular metric with given total mass is a delta function on the Einstein equations and a delta function on the Hamiltonian constraint, the diffeomorphism constraint. And, well, is it possible that this gives rise to a microcanonical distribution like the one we just mentioned? It turns out that it's possible that a primordial fluctuation could do this. If the primordial state was such that it was constant enough on the mass shell, on the solution to the equations of motion, it would give exactly that microcanonical distribution. So the picture is one of large fluctuations in the early universe that, as the universe expands, might be captured by their own trapping horizons and collapse to a black hole. We said there were these two classes of black holes to think about. There were the electromagnetic ones and the ones measured in gravitational waves. Here's a table of the spins of most of the known electromagnetic black holes. And those spins vary over quite a variety of Kerr parameters. So on the bottom of the table, you see an X-ray binary that has, where the final black hole, the black hole number has spin parameter 0.12, all the way up to Cygnus X1, which has a spin parameter greater than 0.95. So on the one hand, we have this prediction from thinking about primordial large fluctuations that maybe some black holes are born spinless. And on the other, we have the X-ray binaries where it's clear that a whole range of spins are possible. So gravitational wave data support one of these kinds of families or the other. A way to characterize that is to imagine the two constituents of a binary as are in state. Those constituents have masses and spin parameters, A's, and they also have an orbital angular momentum. And your final state is going to be your final black hole with its mass and spin and gravitational radiation coming off. In LIGO, it turns out an easier measure is what's called chi-effective. Chi-effective is the mass-weighted average of the spins of the constituents projected onto the orbital angular momentum. And so it turns out that quantity is conserved to the second post-Newtonian order. So this is a very useful quantity to access experimentally. One way to visualize the data of LIGO is to plot the chi-effective on the horizontal and the final spin of the black hole on the vertical. So here are the first three events from the first run. You see some characteristic properties here already. Because the binary has orbital angular momentum, the final spin tends to be in the sort of 0.6 to 0.8 range. And we're starting to see that chi-effective is small. What are possible explanations for that? Because it's a mass-weighted average, it could be that the black holes are anti-aligned, in which case their spins could cancel each other. It could be that the spins are in the orbital plane of the binary, so that the projection kills chi-effective. Or it could be that the spins of the constituents are zero. So there are three ways to get chi-effective of zero. We can add more of the run 01 data. And we can compare this with the proposal of these microcanonical black holes. So in the microcanonical ensemble, we said that black holes are created with zero spin. So all you have is orbital interaction. If the two black holes are equal mass, you can run numerical relativity and you get the red dot in the center. So you would have exactly chi-effective equals 0, and you'd have a final spin of about 0.69. You can also investigate what happens as you change the mass ratio of the two black holes. If one was more massive than the other, the shading will show that on this plot. So lighter shades mean larger mass ratio. Mass ratio is taken as the bigger one divided by the smaller, and so we move down on this plot. The final spin is smaller when you have a mass ratio. And finally, let me include the simulation of when we take one of the constituents to have zero spin. But we imagine the second constituent is second generation. It came, for example, from a merger like the one at the top right. So the merger of those two is going to be one zero spin with one non-zero spin. And again, if you look at this numerically, you can find the blue dots. Again, shading shows the mass ratio, and as you go to lighter shading, you're getting a larger mass ratio. So here's a comparison. If we put the LIGO data on top of the prediction from the microcanonical ensemble, you can see the comparison. And include more data. This is all of the run 1 data. Here's the run 1, run 2, and the first 3 events from 03, the most recent LIGO run. 03 included GW190814, which had a huge mass ratio of about 10. So I've extended the red dots all the way down to mass ratio of 10. And you see that this is the data and this prediction overlay in this interesting way. This top one that's highlighted here is that large mass ratio event. So what can we compare this to? The blue dots, blue and red dots are the microcanonical ensemble that I was just introducing to you. On the right 2 panels are 2 astrophysical models for black hole formation. The center model is like that in a dense globular cluster, where you would expect the black holes to form with essentially arbitrary spin. They call that the isotropic distribution because it's distributed everywhere in space. So if you merge 2 isotropically distributed spinning black holes, you get the purple dots in the center panel. A second model, astrophysical model, is what's called common envelope formation. So you have a large disk of particulate matter, and the black holes form within that rotating disk, and they tend to form in an aligned way with the orbital angular momentum. So the orange dots are formed according to an aligned model. So let's return once more to the idea that we have here. The idea is that these black holes that we are proposing from a microcanonical ensemble may have been formed in the early universe. But it's difficult to get a fluctuation that's large enough that it'll collapse to a black hole. But it becomes exponentially more likely as the pressure on the overdensity reduces. So you can imagine that this would be exponentially enhanced during a phase transition in the early universe. For example, the QCD phase transition, where the equation of state, the pressure drops down during the phase transition, and you get an enhancement of the possibility of production. Correlating those 2 things does something very interesting. You can estimate a mass scale that would come for a black hole that was formed during the QCD phase transition. So I've done the back of the envelope calculation here, and you find an intriguing number. You find 25 solar masses. I find this so interesting because you may remember when LIGO was turned on, people thought that the signal was going to be primarily neutron star mergers. Instead, it's been primarily black hole mergers and black holes that were of a mass range that we hadn't expected. But people had done this calculation and had identified this as an interesting mass window. In fact, if you do more careful calculations in lattice QCD, you find that the mass range can be all the way from a tenth of a solar mass up to 100 solar masses. If we found anything on the bottom end of that range, we would know it was primordial because we can't form those by collapse. But the LIGO black holes are squarely in this range. So LIGO scientists have been looking at this more deeply. Up to now, the measurements and the Bayesian analysis has all looked at chi-effective because, as I said, it's a good parameter for LIGO. But they're starting to ask about the constituent black holes. Can you do an analysis that asks for the Bayesian likelihood of zero-spin members in this population? And such an analysis was done just last year by Gallaudet et al., where instead of just taking a single homogeneous population that has a Gaussian distribution, they broke the population into 2 pieces, a delta function with 0 chi-effective, and a beta distribution for other chi-effectives. And they redid the analysis of the LIGO collaboration. They found this remarkable result on the left. that a large fraction of the LIGO events actually have large Bayesian likelihood for being zero spin. There are some interesting aspects of their analysis that LIGO collaborators have now questioned, and that's what the plot on the right is showing. This is work from just last month, and Callister et al. Redid the analysis where they didn't require a delta function at zero spin, but just did two Gaussian populations. So a Gaussian population that was distributed around non-zero chi-effective and a Gaussian population that's centered around zero chi-effective. So sort of two population or bimodal analysis. What the plot shows is on the horizontal axis you have zeta, which is the fraction of the population that is in the zero spin Gaussian. So, and then the vertical axis shows their PDF, their posterior distribution function on the data, after using the data. And what you find is, well, now it becomes possible that the LIGO data, the LIGO population is characterized by zeta equals 0. But still, the highest values for the PDF are for a fraction between 1/4 and 4/10 of the population. So as many as 1/4 of the LIGO black holes may be in a zero spin population. That's what the collaboration is starting to tell us. This is very interesting for this quantum gravity phenomenology that I was mentioning to you. Here's the full O3 catalog showing all 83 binary black hole mergers and 7 neutron star black hole mergers. The neutron star ones are a little tricky. They don't always know whether it ended up in a neutron star or a black hole. That's why you see several of the dots are colored half and half. But the blue data points at the top of this plot are all black hole mergers. And so now we can take that full population and compare it to this microcanonical proposal coming from quantum gravity. And here's the full catalog for all of those three. Same plot I showed you before, chi-effective on the horizontal, final spin on the vertical. The shaded region is mass ratios between 1 and 4. The dark blue curve at the top of that is a mass ratio of 1. And I find this still quite striking and a very interesting plot to look at. The LIGO data falls almost completely within the microcanonical predictions. There are the 2 points up at the right there that you see that don't fall in this distribution, but they do fall well in the isotropic distribution. I've taken away the aligned distribution, which just doesn't seem to agree with the LIGO data well. So you can compare these two distributions and see what you think of this. We're still probably too few data to really make strong claims, but I think this is a very intriguing proposal for an outcome from quantum gravity. Another thing that I should be careful to say is that by no means am I trying to claim that all the LIGO data are microcanonical. The idea is just that some fraction of them may be of primordial origin, and that fraction should be well described by the microcanonical population. All right, so let me leave you with the most important question for all of you, the question of the observational challenge. How are we going to observe quantum gravity? Well, I don't think what I've shown you is enough to really claim that any of the LIGO black holes are of primordial origin. Right now, all we can do is do this correlation between the mass range, the spin, the chi-effective. This is a very, very interesting correlation to me, but I think you could come up with other explanations for why the LIGO black holes are low spin. So I think what you would really like is a third or a fourth thing to correlate in with the data and to see if you can really separate out those two populations I was just mentioning. Can we find something that tells us, oh, these black holes should be of this variety, and those black holes, they should be of this variety, and further distinguish the data sets? Then the microcanonical ensemble starts to have much more interesting predictive capabilities. Are there more ways to leverage this incredible advent of gravitational wave observations to investigate quantum gravity? There's a number of papers that have been coming out recently, and I think we need to think about this problem deeply, see if we can find a thermostatistical confirmation of quantum gravity. The last several QISS meetings have been very engaged with the question of whether we can observe gravity-mediated entanglement, and I imagine that that's going to continue in this meeting. And are there signs of quantum gravity in the cosmic microwave background or elsewhere in cosmology? There are fascinating proposals about trying to explain the power suppression at large angular separations in the CMB, proposals for using the square kilometer array. But we need to keep thinking about this phenomenological signature. And with that, I'll conclude. Thank you all very much. I've intentionally left us a good chunk of time for discussion, and if you all aren't blown away, then I'm happy for questions or comments. I can repeat your question. Go ahead.
Fluctuations, when you look at that image, appear to be very large, but you mentioned they're very minute, and they are very minute picture, and exaggerates the fluctuations. So people should be aware that that picture is really tiny fluctuation. My question relates to your first presentation, and it's a question I've wanted to go for a long time. You mentioned causal structure. We were talking about how things behave, and we have relational quantum mechanics, and I believe partly at least have causal structure, which might not be able to detect causal structure. So my question is, personal one, do you view it as there being a causal structure? It still gets stated that theoretically, it really matters how you build things if you believe in causal structure.
So there was a comment and a question. The comment was pointing out that the heat map of the CMB is deviations away from the mean. And this is important to note because it can make it look like these deviations are large, but in fact they're quite small because we've subtracted out the overall background. The question was about whether I believe that the causal structure that I'm talking about when I think about these grains of space is fundamental, or whether we need to let go of that as part of our theory and find something underlying it. And my answer is that I meant what I said when I said that the discretization encodes the geometry of the metric. So our discretization carries directly the geometrical observables of our quantum theory of gravity. And intriguingly, those observables that I'm discussing encode enough information to talk about at least the signature of my tetrahedron. So the area variables and the volume are directly encoding enough information for me to reconstruct whether I'm talking about a Euclidean tetrahedron or talking about a Lorentzian tetrahedron. I'm happy to go through this with you in detail. Very roughly, the idea is that the dot products amongst those area variables encode a Gram matrix, and that Gram matrix carries the causal structure encoded in it. So for the moment, I would say that this model carries the causal structure in the same way that gravity does. It's encoded in the metric itself, in the geometry of the spacetime itself.
Okay, this works. In the first part of the talk, you described how the quantum space can undergo tunneling. Describe how one can mathematically describe this from Euclidean to Lorentzian quantum space. My question is this: there is one application in which we've been working, one method in application working, which is to describe the end of the black hole evaporation. And one way of viewing it is tunneling, because the classical equations that are related to the small integration in h bar, presumably something is exponential 1 over h bar squared, something like that. So it's a typical tunneling theorem. Do you think the two things could be related? So could it be that the tunneling one might expect at the end of the black hole from the black hole to the white hole transition could be through some sort of intermediate Lorentzian, Euclidean onto Lorentzian, Lorentzian onto Euclidean, something like that, or is it really?
I am hopeful that is the case. So, and I have two ways of thinking about it, both of which I find very interesting. So I think on the one hand, you have what you were suggesting. I could think about the discrete geometry. I could think about my triangulation and ask directly the question of the triangulation. Ask, does it tunnel, and can I view that tunneling as a transition from a black hole to a white hole? But even at the level of a semi-classical metric, this sort of complexification that I described at the level of the discrete geometry, you can also do at the level of the metric variables. And I wonder if we can do a direct semi-classical sort of Euclidean path integral approach to the black to white hole transition and understand it even at that simpler to compute continuum level. So I'm very interested in both those questions. I don't have a calculation that argues for the positive, but I think it's worth doing those calculations and looking at them. To some extent, spin foam calculations have done so.
Yeah, I think several slides, also here, as you can see, you mentioned you use the term quantum temperature. As a mathematician, I would be interested to know what you mean by that, or maybe elaborate on that.
Sure. So here I meant it in the simple sense that I was just describing of a semi-classical metric. So you can think directly in terms of G mu and the curvature associated with it. But thinking of the title that we gave to the paper was the random geometry. So if all I impose is that the Einstein equations hold and that the ADM constraint holds, then can I think about the set of random geometries that result? So all I'm meaning is the state of those random geometries, probability distribution over them.
So it's some sort of average over all possible derivatives in your ensemble of methods.
Yeah, so for any one given geometry, you could calculate it directly. But yeah, if you wanted to make a statement about the ensemble, you would have to do an average or compute whatever it was you were interested in the ensemble. Yes.
So this is going to be a very naive question from the audience, but does any of the formalism, well, where's the topology comes in? Is it a sort of external information or it grows out of the formalism?
So it depends on your setup. So as I mentioned, often in quantum gravity, we think of this general boundary formulation. So I'm going to specify, the boundary metric at my initial slice and my final slice, and I'm going to specify how I'm pooling those slices on the corner, the codimension 2 boundary of the slices. And so encoded in that boundary metric, you may encode some non-trivial topology, or you may encode a trivial topology. But the question that I was posing was a question of whether the quantum evolution that fills that in transitions through topologies or not. And there I don't have a good answer for you. It's an area of active investigation. And as people have become better and better at dealing with Lorentzian signature triangulations, it's a question that they're actively investigating numerically as well as through theoretical computation.
You mentioned gravity causes collapse. I didn't understand how that engineering wall the qualification. I didn't understand how that entered your talk. Could you clarify that?
Sure. I didn't give any details. You couldn't have possibly understood. But that was more because I was assuming that people knew the story. On this slide, I gave a very heuristic picture of this that needs to be done more carefully in several ways. But what I was pointing out is that there's a back reaction effect that's very important for collapse. So if I have some initial amount of mass that's gravitating, let's say mass m0, well, there's also a pressure holding that mass up. And one of the reasons that this can become a runaway phenomena is that that pressure gives rise to an energy. Pressure times volume gives the energy density, right? So that energy density then contributes to the gravitating mass. So depending on the scale of the region that you're enclosing with matter and self-gravitation, that can become a runaway. If the region is small enough, that feedback just causes the whole thing to collapse. So that's the heuristic argument I'm giving here. You have to go through many, many more careful calculations to show this in full GR.
Yeah, so my question is also a bit more on the alternate side of it. So the probability, the microcanonical probability, do you mind going?
Not at all.
No, the one with the path integral and
Sure.
Yes. So I'm trying to make sense of the denominator here because right now you're doing path integral over all the matters, right? But you're also restricting to the ones that satisfy the Einstein equation. So you're essentially at most will get a semi-classical gravity, right?
That's right. This is a sort of saddle point.
That's right. But if you do the saddle point, right, you probably could get rid of the path integral and just use the stationary phase part, right? So is it? It's not clear to me how from that expression it looks like something that is not Boltzmannian, I guess, because the stationary phase is e to the power minus whatever the action of the stuff, right?
So in fact, so you asked me to come to this slide when I had initially gone to the other one, but that's where this comes from. The saddle point contribution is the Bekenstein-Hawking entropy. And so this is just the expression of that more full quantum gravitational expression in terms of saddle point. That's what we're showing here. And so then that gives rise to this ensemble that I was mentioning. So I'm happy to go through more details with you if you like, but that's exactly the idea.
Hi, thanks for the talk. I've got a question about the mathematical structures you mentioned at the beginning, where you said you can't decompose your system into tensor products all the time. I'm wondering if you could elaborate on what sort of mathematical structures you have, or whether you have some other ways like direct sums or whatever.
Yeah, so there are different approaches, and I was being genuine when I said I wish I understood this better. So let's discuss. Let's see if we can understand better. But the idea is that we're formulating gravity here as a gauge theory, and in gauge theories you have to be very, very cautious and aware of the constraints. And so the reason that this can fail, that you can fail to have a subsystem decomposition, is because the constraint actually connects the two subsystems that you're trying to separate. And if you fail to take that into account, then you've messed up the physics that you're trying to describe. There are ways out of this. So as I was mentioning in electromagnetism, if we take into account the fact that the total charge is written on the boundary, in essence, if we take into account the Coulomb field at the boundary of the region that we're looking at, you can glue the interior region to the exterior region, and you can properly understand the separation of degrees of freedom. But it's not to be, in a gauge theory, it's not to be done casually. You have to look carefully at what you're doing. So all of the underlined references in the talk are hyperlinks, and you can click on things. I highly recommend this work of William Laurent, Dominique Friedel, and Aldo Riello, and Enrique Gomez. They're looking at these things very, very carefully. The physics of what they're finding is still up for discussion. Laurent will tell you that you have an infinite number of charges, and it's very, very tricky to glue. On the other hand, there seems to be some indications from electromagnetism that there's only the global symmetry that you have to be very, very careful about in the gluing. So I'm interested in this question. I want to understand this question much more deeply.
Thanks a lot. We've been working on similar ideas of combining systems that can be converted to subsystems on the foundation. We really have to chat later if you want.
Yeah, I'd be very interested.
Thank you.
There's one here.
Thanks, Hal, for the talk. You mentioned that Einstein had emphasized the role of the synthetic potential in some paper somewhere. Can you elaborate on that?
Yeah, I'm sorry I didn't put the reference in the talk. It's a paper from 1917. I don't remember the title, unfortunately. But at the time, this was still old quantum theory, right? And people were very confused about how to quantize systems with more than 1 degree of freedom. So you could imagine, for example, the Kepler problem or something like that, which we know has a conserved energy, but it also has conserved angular momentum. And so they appreciated very clearly at the time that you'd get a codimension 2 surface in the phase space. So you have a very much reduced part of the phase space that's accessible. But when they tried to quantize it, they weren't sure, should I quantize the energy and the angular momentum, or should I quantize 2 other variables? There's all sorts of ways of cutting up the phase space. And what Einstein realized was that if you took the sum over all your degrees of freedom of P dQi, right, that was a symplectic invariant. If I change to another description of my phase space, I get the same form back, and maybe in the new coordinates, but it's intrinsically geometrically the same. And he also appreciated the topological aspect. So once I know the right thing to work with, I just integrate it along the independent cycles. This is just uncomplexified. This is just the normal phase space. If I integrate that along the 2 independent cycles in this Kepler problem, I get 2 quantization conditions, and they're always the physically right ones. It doesn't matter what my choice of cycle is. Or they could be linear combinations of the right ones, but that's fine. There's no issue with that. So it was a deep appreciation of the symplectic invariance of the symplectic potential and of the topology of the quantization condition. The reason it led to inventing quantum chaos is he realized if I don't have a nice integrable distribution in my phase space, how am I going to get nice closed cycles? And he appreciated that in general you're not. And it's much, much harder to quantize chaotic systems. Secretly in there, Pierre has pointed out a weakness in my argument for this tunneling of geometry. If we get enough degrees of freedom, right, then the gravitational description of that large number of degrees of freedom is going to become chaotic, presumably. And it's going to be much harder to make the mapping that I just was mentioning, this Picard-Fuchs sort of relation. But I think that's an area of active interest in the resurgence community. If we have a chaotic system, is there still things we can say about perturbative, non-perturbative relations?
It's about time.
Wonderful.
This wonderful session.
Thank you very much.
Thank you. Thank you so much. Oh, sorry.
Go ahead.
Well, let's not be both. So, thanks again to Hal for the wonderful lecture. I encourage everybody, and I encourage in particular the youngest among the participants to don't be shy and raise their hands to ask questions during these lectures. These lectures are especially meant for you, so please don't hesitate. And we are going into the coffee break in a second. I just wanted to share a couple of announcements. The first one is that some people need to connect to internet. You should be able to use your university account with EduRoam. If you haven't done this, you have to put your official institutional email complete, and then just use your passwords, the usual password of the university. You should be able to connect. If it doesn't work, there is an alternative. So there are forms there that you can use to have a password, an account that you can use during the conference. So this will work. It's a personal one. You will have the credentials to access with multiple devices, so you can use it both on your phone, on your computer, and on your tablet. The important thing is that you can fill the form that is at the reception, and you have to give back us the bottom of the form, okay? That's the first important thing. The second important thing is that many of you have requested the printing of the poster, so I would like to announce that the poster will be available here during the lunch break. So if you order a poster during the lunch break around noon, please reach the reception and we will hang together your poster. And yeah, I just wanted to remind everybody that, of course, the mask is compulsory inside, and maybe we can profit for some fresh air during these breaks. But now it's time for coffee and for cakes and to relax and have a lot of chats. And for those who have already the poster there, everybody is invited during all the breaks to go to the posters and have chats with the authors of the posters. Thank you.